Hello. Welcome back to Drowsy Inquirer. Tonight, we are going to think about numbers, not in the way you might remember from school, not with tests or formulas or any pressure at all. We are simply going to wander through one of the oldest and most beautiful ideas in human thought, the idea of prime numbers. A prime number is something wonderfully simple. It is a number that can only be divided evenly by one and by itself. That is all. And yet, from this simple definition comes a universe of mystery and elegance that has captivated human minds for thousands of years. So let your body settle. Let your thoughts slow down. We are not solving anything tonight. We are not memorizing anything. We are simply walking through a quiet garden of numbers, noticing their patterns, appreciating their strange beauty, and letting the gentle logic of mathematics carry us toward rest. There is something deeply calming about prime numbers. They are certain. They are unchanging. They have been the same since before humans existed, and they will remain the same long after we are gone. In a world full of chaos and unpredictability, prime numbers offer a kind of anchor, a reminder that some things are simply eternally true. Let us begin with the very first primes and see where they take us. Imagine you have a collection of stones, 12 stones, let us say. You can arrange these 12 stones in many different ways. You could make 2 rows of 6, or 3 rows of 4, or 4 rows of 3, or 6 rows of 2. 12 is a flexible number. It can be divided evenly in many ways. Now imagine you have 7 stones. You try to arrange them into equal rows, but something interesting happens. You cannot make 2 equal rows, because 7 divided by 2 leaves a remainder. You cannot make 3 equal rows, or 4, or 5, or 6. The only way to arrange 7 stones into equal rows is to make 1 row of 7, or 7 rows of 1. 7 is a prime number. It cannot be broken down into smaller equal parts. It is indivisible in a fundamental way. This is the essence of primality. A prime number stands alone. It cannot be expressed as the product of 2 smaller numbers. It is, in a sense, a building block, an atom of arithmetic. The number 1 is special and is not considered prime. It is the unit, the starting point, but not a prime itself. The first prime number is 2. It is also the only even prime, because every other even number can be divided by 2. After 2 comes 3, then 5, then 7, then 11, then 13. There is something pure about these numbers. They have no hidden factors, no secret divisors. What you see is what you get. A prime number is honest in a way that other numbers are not. It carries no baggage, no complexity. It simply is. As you lie there tonight, think of prime numbers as islands in a vast sea of integers. Most numbers can be broken apart, reduced, factored into smaller pieces. But the primes remain whole. They are the solid ground upon which all other numbers are built. Let us count the early primes together. Not quickly. There is no rush. Just a gentle walk through the beginning of an infinite sequence. 2, the smallest prime, the only even one. A pair, a couple, the beginning of plurality. 3, the first odd prime. A triangle has 3 sides. Many ancient cultures considered 3 a sacred number. 5, our hand has 5 fingers. A pentagon has 5 sides. There is something pleasing about 5. 7, a week has 7 days. Many traditions speak of 7 as a number of completeness. 11, the first prime that requires 2 digits to write, a small leap forward. 13, often called unlucky, but mathematically it is simply the next prime, neutral and unchanging. 17, 19, 23, 29, 31. Notice how they arrive irregularly. There is no simple pattern telling us when the next prime will appear. After 2, the gap to 3 is just 1. After 3, the gap to 5 is 2. After 7, we jump to 11, a gap of 4. After 23 comes 29, a gap of 6. The primes are unpredictable in their spacing, yet absolutely determined in their identity. We cannot know easily where the next one will be, but once we find it, there is no doubt. It either is prime or it is not. There is no ambiguity, no debate. This combination of unpredictability and certainty is part of what makes primes so fascinating. They are wild, yet tame, random, yet fixed. They follow rules we do not fully understand, yet they never break those rules. Let the rhythm of the early primes be a kind of lullaby. 2, 3, 5, 7, 11, 13. Ancient numbers, eternal numbers, numbers that have been the same since the beginning of the universe. 23 centuries ago, in the ancient Greek city of Alexandria, a mathematician named Euclid wrote a book. It was called The Elements, and it became one of the most influential texts in human history. In this book, Euclid collected and organized the mathematical knowledge of his time, presenting it in a logical, step-by-step fashion. Among the many treasures in Euclid's Elements is a proof about prime numbers, a simple, elegant argument that demonstrates something profound. There are infinitely many prime numbers. No matter how far you count, you will never run out of primes. The proof is beautiful in its simplicity. Imagine, Euclid said, that there were only a finite number of primes. Suppose we could list them all, call them P1, P2, P3, and so on, up to some final prime, Pn. Now, said Euclid, consider a new number. Take all of these primes and multiply them together, then add 1. What can we say about this new number? It cannot be divisible by any of the primes on our list. When you divide it by P1, you get a remainder of 1. When you divide it by P2, you get a remainder of 1. The same for every prime on the list. So, either this new number is itself prime, or it has prime factors that were not on our original list.
Either way, we have found a prime we missed. This contradicts our assumption that we had listed all the primes. Therefore, our assumption must be wrong. There cannot be a finite list of all primes. There must be infinitely many. 23 centuries later, this proof remains just as valid. It has not aged. It has not been improved upon. It simply is. There is something restful about infinity when approached this way. The primes go on forever. No matter how large a number you name, there are primes beyond it. The sequence never ends. It stretches out into eternity, patient and unending, like the night sky full of stars.
Not long after Euclid, another Greek thinker developed a method for finding prime numbers. His name was Eratosthenes, and he lived in Alexandria as well. He was a polymath, interested in geography, astronomy, poetry, and mathematics. He is said to have calculated the circumference of the Earth with remarkable accuracy. But tonight, we remember him for something simpler, a method for sifting out prime numbers called the Sieve of Eratosthenes. Imagine you write down all the numbers from 2 to 100, a grid of integers waiting to be sorted. You begin with 2, the first prime. You circle it. Then you cross out every multiple of 2, 4, 6, 8, 10, and so on. All the even numbers except 2 itself. Now you move to the next number that has not been crossed out. That is 3. You circle it. Then you cross out every multiple of 3 that remains. 6 is already crossed out. 9 is not, so you cross it. 12 is already gone. 15, cross it out, and so on. The next uncrossed number is 5. Circle it, then cross out 15, 25, 35. Many of these are already crossed out from earlier steps. You continue this process, 7, 11, 13. Each time you circle the prime and remove its multiples. When you are done, what remains? Only the circled numbers, only the primes. The Sieve of Eratosthenes has filtered out all the composite numbers, leaving the primes behind like gold dust after washing away sand. There is something meditative about this process, the repetition, the gradual clarification, starting with a jumble of numbers and slowly, patiently revealing the primes hidden within. It is like clearing a garden of weeds one by one until only the flowers remain. The Sieve of Eratosthenes is over 2,000 years old, yet it still works perfectly. A simple algorithm, timeless and true. Let its rhythm carry you deeper into relaxation. Circle, cross out, circle, cross out. The primes emerge one by one, eternal and unchanging. Prime numbers are not just abstract ideas living in the minds of mathematicians. They appear in the natural world as well, woven into the fabric of life itself. Consider the cicada. These insects live underground for years, feeding on tree roots in darkness. Then, all at once, they emerge in vast numbers, fill the air with their song, mate, lay eggs, and die. Their children burrow back into the ground, and the cycle begins again. What is remarkable is the length of these cycles. Some cicada species emerge every 13 years,
others every 17 years. 13 and 17 are both prime numbers. Why would nature choose prime number cycles? Scientists believe it has to do with predators and competition. If a cicada had a 12-year cycle, it would synchronize with predators that have 2-year, 3-year, 4-year, or 6-year cycles. But with a 13-year cycle, synchronization is rare. The primes protect the cicadas by making their emergence unpredictable. Flowers also show a preference for numbers related to primes. Count the petals on many flowers, and you will find 3, 5, 8, 13. These are Fibonacci numbers, closely related to primes and the golden ratio. A lily has 3 petals. A buttercup has 5. A daisy often has 13, 21, or 34. The spirals in a sunflower head follow Fibonacci patterns as well. The seeds arrange themselves in interlocking spirals, with the numbers of spirals in each direction often being consecutive Fibonacci numbers. This arrangement allows the maximum number of seeds to fit in the available space. Nature, it seems, discovered the beauty and utility of these numbers long before humans did. The primes and their relatives are not human inventions. They are discoveries. They were waiting in the structure of reality, patient and eternal, for us to notice them. As you rest tonight, imagine a field of sunflowers swaying in a gentle breeze. Each flower head a spiral of mathematical perfection, each seed arranged according to principles older than life itself. The numbers are there, hidden in the petals, whispering their secrets to anyone who cares to look.
Among the prime numbers, there are special pairs that have captured the imagination of mathematicians for centuries. They are called twin primes, 2 prime numbers that differ by exactly 2. 3 and 5 are twin primes. So are 5 and 7, 11 and 13, 17 and 19, 29 and 31, 41 and 43. There is something touching about twin primes. In the vast landscape of numbers, these pairs stand close together, separated by only a single even number. They are companions in the infinite sequence, neighbors in the numerical universe. As numbers grow larger, prime numbers become less frequent. They thin out like stars at the edge of a galaxy. You might expect twin primes to eventually disappear altogether, the gaps between primes growing too large to allow such close pairs. And yet, as far as we have searched, twin primes keep appearing. We have found enormously large twin primes, pairs of numbers with thousands of digits still standing just 2 apart. Do twin primes go on forever? This is one of the great unsolved problems in mathematics. We believe they do. Everything we have observed suggests they continue indefinitely, but we have not proven it. The question remains open, a gentle mystery waiting for resolution. There is comfort in unsolved problems when approached the right way. Not every question needs an answer tonight. Some mysteries are meant to be savored, admired, held lightly in the mind without grasping. The twin prime conjecture is such a mystery, beautiful in its simplicity, profound in its implications, still waiting, after all these years, for someone to unlock its secret. For now, let us simply appreciate the twin primes, those paired travelers walking together through infinity. 3 and 5, 11 and 13, companions on an endless road.
If you walk along the number line, Stepping from one prime to the next, you will notice something curious. The distances between your steps are not regular. Sometimes you step just 2 numbers forward. Sometimes you leap across a much larger gap. After 2 comes 3, a gap of 1. After 3 comes 5, a gap of 2. After 7 comes 11, a gap of 4. After 23 comes 29, a gap of 6. After 89 comes 97, a gap of 8. As numbers grow larger, the gaps tend to grow as well. Primes become less dense, more scattered. The average distance between consecutive primes increases slowly, logarithmically, as you move further along the number line. And yet, even among enormous numbers, you can still find primes surprisingly close together. Twin primes, as we discussed, are separated by only 2. Cousin primes are separated by 4. Sexy primes by 6. These small gaps persist even as the primes themselves become rare. There are also prime deserts, long stretches of consecutive numbers where no primes are found. You can construct arbitrarily long deserts if you know where to look. For any number n, there exists a sequence of n consecutive composite numbers with no primes among them. The primes are distributed unevenly, clustered in some regions, sparse in others. This irregularity is part of their charm. They do not march in lockstep. They wander, gathering sometimes, dispersing at other times, following rules that we glimpse but do not fully comprehend. Think of the primes as fireflies in a summer field. Sometimes they cluster together, their lights blinking in close proximity. Sometimes one drifts alone through the darkness, far from its nearest neighbor. There is pattern in their movement, but also randomness, order and chaos intertwined. As you drift toward sleep, let the gaps between primes be like the gaps between thoughts. Sometimes your mind moves quickly, one idea close to the next. Sometimes there are long pauses, quiet stretches where nothing seems to happen. Both are natural. Both are part of the rhythm.
Some mathematicians speak of the primes as having a kind of music. Not literal music, of course, but a rhythm, a structure, an underlying harmony that can be felt, if not quite heard. The distribution of prime numbers follows patterns that echo the patterns of sound waves and musical notes. There are frequencies and harmonics hidden in the sequence of primes. Mathematicians have even translated primes into actual sounds, creating eerie, beautiful compositions from their sequences. If you were to plot the primes on a number line and listen to them as a melody, what would you hear? Not a simple tune, not a predictable rhythm, something more complex, something that sounds almost random at first, but reveals structure the longer you listen. The mathematician Bernhard Riemann discovered deep connections between prime numbers and certain wave-like functions. His work suggested that the primes, despite their apparent randomness, are controlled by an underlying order, a kind of cosmic music playing just beneath the surface of arithmetic. There is a hypothesis named after Riemann that describes this hidden order. It remains unproven after more than a century and a half.
If proven, it would reveal the deepest secrets of prime distribution. It would be like finally hearing the full symphony after catching only fragments and echoes. But even without the complete answer, we can appreciate the music that is already audible. The rhythm of the primes, the way they cluster and scatter, the surprising harmonies that emerge when you look at them from the right angle. Tonight, let the music of primes be a background hum, not loud or insistent, just a gentle presence, like distant wind chimes or the murmur of a stream. The numbers are singing their ancient song, and you are drifting on its melody.
Thousands of years ago, people looked at numbers and asked the same questions we ask today. What makes some numbers special? Why do certain patterns appear? Is there an order beneath the apparent chaos? In ancient Babylon, scribes pressed cuneiform symbols into clay tablets, recording numbers and calculations. Some of these tablets, preserved for millennia, show sophisticated understanding of arithmetic and geometry. The Babylonians knew about squares and cubes, about fractions and equations. Did they also wonder about primes? In ancient Egypt, mathematicians calculated with precision, designing pyramids and tracking the flooding of the Nile. Their number systems were practical, focused on measurement and commerce. But surely some curious mind, gazing at the stars above the desert, also contemplated the nature of number itself. In ancient Greece, mathematics became a discipline in its own right. Pythagoras and his followers believed that numbers were the key to understanding the universe. They discovered irrational numbers, geometric theorems, and yes, the special nature of primes. For the Pythagoreans, mathematics was almost a religion, a path to truth and harmony. In ancient India, scholars developed the number system we use today, including the revolutionary concept of zero. They explored infinite series, algebraic equations, and the properties of integers. Prime numbers were known and studied, part of the vast landscape of mathematical thought. In ancient China, mathematicians worked on similar problems, developing their own methods and discoveries. The Chinese remainder theorem, still used today in number theory and computer science, dates from this period. Across cultures and centuries, humans have been drawn to the same questions. The prime numbers do not belong to any one civilization. They are universal, discovered independently by different peoples at different times. They were waiting to be found, like mountains or rivers, features of a landscape that exists beyond any individual mind. Tonight, as you rest, you join a long tradition. Countless people before you have contemplated these same numbers. Countless more will do so after you are gone. There is something comforting in this continuity. The primes connect us to our ancestors and our descendants alike. One of the beautiful things about prime numbers is how simple they are to define. A prime is a number greater than 1 that has no divisors other than 1 and itself. A child can understand this, and yet from this simple definition flows an ocean of complexity. The greatest mathematicians in history have devoted their lives to understanding primes. Some of the hardest unsolved problems in mathematics concern these elementary objects. The contrast between the simplicity of the definition and the difficulty of the resulting questions is profound.
This pattern appears throughout mathematics. Simple rules, complex consequences. The game of chess has straightforward rules that can be learned in an hour, yet the game itself is inexhaustibly deep. The Mandelbrot set is defined by a simple formula, yet its boundary is infinitely intricate. Prime numbers are defined in a single sentence, yet they have occupied human minds for millennia. There is a lesson here, perhaps. Complexity need not come from complicated beginnings. The richest structures can emerge from the simplest seeds. A few basic principles, applied consistently, can generate endless variety. This might be true of life as well. A few core values, held steadily, can guide a person through infinite situations. A few genuine relationships can provide more richness than 1,000 shallow ones. Simplicity at the foundation, complexity in the flowering. As you lie there tonight, let your mind simplify. Let go of the complicated, the tangled, the overwhelming. Return to basics. Breath in, breath out. One moment, then the next. Simple truths endlessly unfolding. The prime numbers have been teaching this lesson for eons. They are simple and they are infinite. They are defined in a breath and they fill the universe. Perhaps we can learn from Tim. Perhaps we can find peace in their quiet, eternal logic.
In the 17th century, a French monk named Mersenne corresponded with the greatest mathematical minds of his era. He was a humble man, more interested in connecting thinkers than in seeking fame for himself. But his name became attached to a special family of prime numbers that still bears it today. Mersenne primes have a particular form. They are one less than a power of 2. 2 to the power of 2 is 4. Subtract 1 and you get 3, which is prime. 2 to the power of 3 is 8. Subtract 1 and you get 7, which is also prime. 2 to the power of 5 is 32. Subtract 1 and you get 31, another prime. Not every number of this form is prime. 2 to the power of 4 is 16. Subtract 1 and you get 15, which is divisible by 3 and 5. So 15 is not a Mersenne prime. The pattern is selective. Only certain exponents produce primes. What makes Mersenne primes special is their connection to perfect numbers. A perfect number is one that equals the sum of its proper divisors. 6 is perfect because 1 plus 2 plus 3 equals 6. 28 is perfect because 1 plus 2 plus 4 plus 7 plus 14 equals 28. Every even perfect number corresponds to a Mersenne prime. This connection was known to Euclid, though the full proof came later. The relationship binds these two families of numbers together in an elegant dance, each one implying the other. As of today, only 51 Mersenne primes have been discovered. The largest known prime number is almost always a Mersenne prime, found by networks of computers searching through vast numerical landscapes. These searches continue even now, volunteers around the world donating their computing power to find the next giant prime. There is something peaceful about this collective effort, people united not by politics or commerce, but by curiosity, searching together for something that has no practical value, only beauty.
The next Mersenne prime is out there, waiting to be found, enormous beyond comprehension, patient and eternal.
How big is the biggest prime number we know? The answer changes every few years as new discoveries push the boundary further. But to give you a sense, the current record holder has over 24 million digits. 24 million digits! If you tried to write this number out by hand, 1 digit per second, it would take you more than 9 months of continuous writing. If you printed it in a book with 1,000 digits per page, the book would have over 24,000 pages. And yet, in the infinite realm of numbers, this giant is still near the beginning. No matter how large a prime we find, there are always larger ones waiting. The search never ends because it cannot end. Finding these enormous primes requires sophisticated algorithms and powerful computers. The great Internet Mersenne prime search, known as GIMPs, coordinates thousands of volunteers who donate their computers' idle time to the hunt. When a new candidate is found, it is verified multiple times before being announced. The mathematical community celebrates each discovery like the sighting of a rare bird. But here is the beautiful thing. The size of these primes does not make them more prime than smaller ones. 2 is just as prime as a number with 24 million digits. Primality is not a matter of degree, it is absolute. A number either is prime or it is not. The smallest and largest primes share the same fundamental nature. This equality is comforting. In a world obsessed with size and quantity, the primes remind us that some qualities are not diminished by scale. A small act of kindness is just as kind as a large one. A simple truth is just as true as a complicated one. The essence remains, regardless of magnitude. Every time you make a purchase online, every time you send a private message, every time you access your bank account, prime numbers are working silently to protect you. Modern cryptography, the science of keeping information secure, relies heavily on prime numbers. The most common method, called RSA encryption, uses the simple fact that multiplying 2 large primes is easy, but figuring out which primes were multiplied is extraordinarily hard. Imagine someone gives you the number 15 and asks you to find its prime factors. Easy, 3 times 5. But what if they gave you a number with 300 digits? Finding its factors could take longer than the age of the universe, even with the fastest computers. This asymmetry, easy to multiply but hard to factor, is the foundation of much of our digital security. Your credit card number, your passwords, your private communications are all protected by the humble prime numbers, standing guard like silent sentinels. It is strange to think about. These abstract mathematical objects, studied by ancient Greeks for their beauty, now keep our modern world running. Euclid could never have imagined online banking, yet the primes he contemplated are the very same primes securing your transactions tonight. There is a lovely continuity here. Mathematics done for its own sake, for the sheer joy of understanding, turns out to have practical applications centuries later.
The pursuit of knowledge is never wasted. Truth has a way of becoming useful, even when that was never the intention. As you rest, know that the primes are watching over you, not just as abstract ideas, but as practical guardians. They have been trustworthy for thousands of years. They will remain so for thousands more.
In 1963, a mathematician named Stanislaw Ulam was sitting in a boring meeting. To pass the time, he began doodling. He wrote the number 1 in the center of a piece of paper, then spiraled outward, writing 2, 3, 4, 5, and so on in a growing spiral pattern. Then, almost absent-mindedly, he circled the prime numbers. 1 was not circled, 2 was circled, 3 was circled, 4 was not, 5 was circled, and so on, around and around the spiral. When Ulam stepped back and looked at his doodle, he noticed something unexpected. The primes were not scattered randomly. They seemed to cluster along diagonal lines. Patterns emerged from the chaos, visible to the eye, even without calculation. This discovery, now called the Ulam spiral, revealed hidden structure in the distribution of primes. The diagonal lines correspond to certain polynomial formulas that produce unusually many primes. The visual pattern hinted at deep mathematical truths that are still being explored today. There is something magical about Ulam's story, a moment of boredom leading to genuine discovery, a simple doodle revealing cosmic order. It reminds us that insight can come from anywhere at any time, often when we least expect it. The Ulam spiral also shows us that the primes, for all their apparent randomness, are not truly random. There is structure hidden within their distribution. We may not fully understand it yet, but it is there, waiting to be uncovered. Imagine the spiral now, numbers coiling outward like a galaxy, primes glowing along diagonal lines, a pattern emerging from apparent disorder. The universe speaks in mathematics, and sometimes, if we are quiet and patient, we can hear what it is saying. As you travel further along the number line, primes become less frequent. Among the first 100 numbers, there are 25 primes. Among the first 1,000, there are 168. Among the first 1,000,000, there are 78,498. Is there a pattern to this thinning? Can we predict, roughly, how many primes exist below a given number? In the 19th century, mathematicians discovered that there is indeed a pattern. The number of primes below a given number is approximately that number divided by its natural logarithm. This relationship, called the prime number theorem, describes the average density of primes with remarkable accuracy. The theorem does not tell us exactly where the primes are. It does not identify specific primes or predict gaps, but it gives us a sense of the overall landscape. Primes thin out gradually, becoming rarer and rarer, but never disappearing entirely. There is something reassuring about this gradual thinning. The primes do not vanish abruptly. They fade slowly, like stars at the edge of vision. No matter how far you travel, there are always more primes ahead, just becoming harder to find. The prime number theorem was proven independently by two mathematicians in 1896, after decades of effort by many brilliant minds.
Its proof required deep insights into analysis and complex numbers, far beyond simple arithmetic. Yet the statement itself is elegant and accessible. The density of primes follows a smooth, predictable curve. Order underlies the apparent chaos. The primes may seem scattered, but their overall distribution obeys a gentle law. This is one of the great themes of mathematics. Beneath the apparent complexity lies deeper simplicity. Beneath the randomness lies hidden order.
Throughout history, certain individuals have devoted their lives to understanding prime numbers. Their stories are as varied as humanity itself, yet united by a common love for these fundamental objects. Carl Friedrich Gauss, often called the Prince of Mathematicians, became fascinated with primes as a teenager. By 15, he had already made observations about their distribution that would later become the prime number theorem. He kept tables of primes computed by hand and saw patterns that others missed. Bernhard Riemann, a shy and sickly genius, wrote a single short paper on prime numbers in 1859. That paper contained the famous Riemann hypothesis, which remains unsolved to this day. Riemann died at 40, leaving behind fragments of brilliance that mathematicians are still piecing together. Srinivasa Ramanujan grew up poor in India, teaching himself mathematics from borrowed books. He filled notebooks with formulas and theorems, many involving prime numbers, that astounded the European mathematicians who eventually discovered him. His intuition was almost supernatural, his creativity boundless. Paul Erdős was a Hungarian mathematician who lived out of a suitcase, traveling the world, collaborating with everyone he met. He published more papers than any mathematician in history, many about prime numbers. He famously said that a mathematician is a machine for turning coffee into theorems. These were not distant gods, but real people. They struggled, doubted, failed, and persisted. They were driven by curiosity and wonder, not fame or fortune. They found joy in the pursuit of understanding, in the moment when confusion transforms into clarity. Their work lives on. Every student who learns about primes is connected to Gauss and Riemann, to Ramanujan and Erdős. The chain of knowledge stretches back through centuries and forward into the future. We are all part of this chain. Prime numbers are eternal. They existed before the earth was formed. They will exist after our sun has burned out. They are not subject to time in the way that physical objects are. This is a profound thought, if you let it settle. The number 7 was prime in the age of the dinosaurs. It was prime when the first humans looked up at the stars. It will be prime 1 trillion years from now, when everything we know has turned to dust. Mathematics exists outside of time. It is not invented, but discovered. The truths of mathematics are waiting for us, independent of human activity. We may be the first to notice a particular theorem, but the theorem was already true before we noticed it. This gives mathematics a strange kind of permanence. Fashions change, empires rise and fall, languages evolve beyond recognition, but the prime numbers remain exactly as they are. They are anchors in the storm of time, fixed points in a universe of change.
When you contemplate a prime number, you are touching something timeless, the same number contemplated by Euclid and Gauss and Ramanujan, the same number that will be contemplated by minds 1,000 generations hence. There is a continuity here that transcends individual lives. Tonight, as you lie in the darkness, let this thought be a comfort. You are connected to something eternal. The primes have always been and always will be. For a moment you share in their timelessness. You rest in the calm that comes from touching the infinite.
Mathematicians often speak of proofs as beautiful. This may seem strange to those outside the field. How can an argument be beautiful? But to those who have experienced it, mathematical beauty is as real and powerful as any other kind. A beautiful proof has several qualities. It is clear, each step following inevitably from the one before. It is surprising, revealing connections that were not obvious. It is economical, using no more than is necessary. And it is true, unshakably, eternally true. Euclid's proof that there are infinitely many primes is considered one of the most beautiful proofs ever written. It is short, just a few lines. It uses only the most basic properties of numbers, and yet it establishes something vast and eternal. From almost nothing, infinity emerges. There are many proofs in mathematics. Some are long and technical, understandable only to specialists. But the greatest proofs share a quality of elegance that speaks to everyone. They are like poems, dense with meaning, rewarding repeated contemplation. Learning to appreciate mathematical beauty takes time and exposure, but it is available to anyone willing to make the effort. You do not need advanced degrees or special talents. You need only patience, curiosity, and an open mind. Tonight you have heard several beautiful ideas. The infinity of primes, the sieve of Eratosthenes, the dance of twin primes. Each of these is a small gem, polished by centuries of thought, offered freely to anyone who wishes to appreciate it. Beauty is a form of truth, and truth is a form of beauty. In mathematics, the two are inseparable. Let this thought accompany you into sleep. The universe is beautiful, and you are part of it.
Perhaps it is fanciful, but the prime numbers can serve as metaphors for life. Their properties echo truths that extend beyond mathematics. Primes are indivisible. They cannot be broken down into smaller factors. In life, too, there are things that are fundamental, irreducible, not to be compromised, core values, essential relationships, the parts of ourselves that we must protect and preserve. Primes are rare. They thin out as numbers grow larger. The precious things in life are also rare. Genuine friendship, deep understanding, moments of perfect peace. These cannot be manufactured or rushed. They arrive on their own schedule, like primes along the number line. Primes are unpredictable. We cannot easily forecast where the next one will appear. Life, too, surprises us. Joy comes from unexpected quarters. Challenges arise without warning. We cannot control the sequence, only respond to it with grace. And yet, primes follow hidden laws.
Their distribution obeys patterns we are still uncovering. Life, too, may have an underlying order, a meaning we glimpse but do not fully comprehend. We trust that the universe makes sense even when we cannot see how. These parallels are not rigorous. They are poetic, suggestive, meant to inspire rather than prove. But perhaps that is their value. Mathematics and life are not so far apart. The same qualities that make primes fascinating, their simplicity and depth, their rarity and persistence, their mystery and order, are the qualities that make life rich. As you drift toward sleep, consider what is prime in your own life, what cannot be divided, what stands alone, fundamental and pure. Hold these things gently in your mind. They are your anchors, your own eternal truths.
We have traveled far tonight, from the first primes 2 and 3 to the giants with millions of digits, from ancient Greece to modern computer searches, from simple definitions to unsolved mysteries. And yet, we have only scratched the surface. The world of prime numbers extends infinitely in all directions. No matter how much we learn, there is always more to discover. The road has no end. This is the nature of mathematics. Each answer opens new questions. Each peak reveals higher mountains beyond. The journey is perpetual, the horizon always receding. And this is as it should be. A finite mathematics would be a dead mathematics. The infinite unknown is what keeps it alive. There is peace in accepting the infinite. We will never know everything. We will never solve every problem, but we can walk the road step by step, enjoying the journey without demanding a destination. The walking itself is the reward. Prime numbers teach us this lesson. They go on forever. We cannot count them all, but we can count the first few and the next few and the few after that. We can enjoy each one as we encounter it, without worrying about the uncountable many we will never reach. Life is similar. We cannot experience everything. We cannot meet everyone, visit every place, think every thought. But we can savor what we do experience. We can be present to the moment, appreciating each day as it comes, without mourning the infinity of days we will never see. Tonight, let the endless road of primes be a comfort, not a burden. Infinity is not emptiness. It is fullness beyond measure. There is always more, and that is wonderful. The hour has grown late. Our journey through the land of prime numbers is drawing to a close. We have wandered together through ancient proofs and modern mysteries, through nature's patterns and human stories, through the simplest of definitions and the deepest of truths. Prime numbers, those indivisible atoms of arithmetic, have accompanied humanity for thousands of years. They were here before us, and they will remain long after. They are woven into the fabric of reality, as fundamental as space and time. Tonight, we have not solved any problems. We have not memorized any formulas. We have simply wandered and wondered, letting the quiet logic of mathematics wash over us.
And perhaps in that wandering we have found a measure of peace. There is comfort in certainty. Prime numbers are certain. 2 is prime today, and it will be prime tomorrow, and it will be prime 1,000,000 years hence. In a world of constant change, they offer something fixed, something reliable, something true. As you drift toward sleep, carry this certainty with you. Let the primes be like stars in your mind, bright points of unchanging light in the darkness. They have guided travelers before you, and they will guide travelers after. They are patient friends, asking nothing, offering everything. The numbers are infinite, and so is the night. But you are here, now, in this moment, resting in the calm that mathematics provides. The logic is gentle. The truth is peaceful. The primes are watching over you. Thank you for joining me on this quiet journey. Thank you for letting your mind wander through these ancient ideas. Sleep well. Let the eternal numbers carry you into dreams. Good night from Drowsy Inquirer.